Okay. All right. I think we're good. So, hello everyone. Welcome back to Concrete 30. I hope you had a nice break full of reading. Before we start, hello. Before we start today's topic, I'd like to make some quick admin announcements since it's been maybe a bit that you haven't thought about 330. So just some quick announcements before we get started. So just a reminder that midterm 2 is coming up and is scheduled for November 4th. So it's been pushed a little bit in case you hadn't noted. The content is going to be on context-free languages. So everything up until the end of the context-free language sort of chapter. So that's going to be maybe a couple more lectures. And in terms of the problem sets, this is going to include problem set 3, which has already been released, and also problem set 4, which will be released fairly soon. Okay, so any questions about admin before we get started? Yeah. Tutorial. Oh, yeah. Tutorial solutions for problem set 3 this weekend. Yeah. And problem set 4 should be posted by early next week. Yeah, good question. Yeah. Yes, we have a tutorial on Thursday. Yes, I'll be there. Hopefully, not just the tutorial leader will be there. Good. Yeah. Any other questions? No, it doesn't look like it. Okay, cool. So the topic for today will be the equivalence of context-free grammars and push-down automata. Okay, so we're going to actually see today. I don't think we're actually going to have the time to finish the entire sort of proof, but we're going to see that actually context-free grammars, which you've seen a lot about, and PDAs, which you've seen a bit about, are actually sort of equivalent in terms of expressive power. But because you might be a bit rusty on your context-free grammars and PDAs, I don't expect that everyone here to have studied only 330 during the break. I'm going to give you a quick review of both of these things, just so that we're on the same page. Okay. So first of all, let's try to remember what are these things known as context-free grammars. Right. So at a very high level, context-free grammars are essentially language generators, right? So they are language generators. So you can imagine you have some grammar G, and this grammar G is like spitting out strings, right? It's just spitting out strings in some way. You get W1, that's one string. You get W2, that's another string, and so on. And the set of all strings generated by the grammar is L of G, right? Okay, and so how does this actually work? Like, what is the mechanism behind generating strings? Well, it's through production rules and derivations. Okay, so let's look at a simple example of this. So suppose I have the grammar S, which is a start variable, gives me A as B or AB. So here I have two production rules, right? I have two production rules. S gives me A as B, and S gives me AB, right? Now I can use these production rules to generate strings. So how do I do this? I do this via derivations. So for instance, I can generate AB by doing something like S gives me AB, right? I can generate something like A squared B squared by doing something like S gives me A as B, taking this S, right? And now instead of, well, here in this case, I replace S by A as B. And now here I actually do this replacement here, right? So I replace S with AB here. So I get A, AB, B. So this is A squared, B squared, right? And in general, after some number of derivation steps, right? After some number of derivation steps, I'm going to be able to generate any string that looks like AN, BN for n greater or equal to 1. Okay, so this is the language generated by G, where G is just this grammar here. Okay, so these are grammars, right? This is what you've been seeing for a few lectures now. There's some interesting properties about context-free grammars. One of them is that you can also represent derivations, not just in this sort of linear fashion, but also with parse trees, right? So there's this notion of parse trees. So parse trees of context-free grammars, right? So parse trees are tree representations of string derivations, right? So for instance, if I wanted to represent S gives me a squared b squared via a parse tree, then I could say, well, my root node is always going to be the star variable, so it's going to be S. Then S can derive A S B, so each of these are going to be individual nodes. A and B are going to be leaf nodes, so I'm going to get A, S, and then B. And then S, again, here, S is an internal node because it's a variable. All variables in parse trees are actually internal nodes. All terminals are leaf nodes. So then S here is going to be replaced by A and then B. And so we can see that, if we sort of read this tree in a sort of depth first search kind of way, then we get, A, so we get A, B, B. So this is known as the yield of the parse tree, right? And the yield of the parse tree is the string generated by the grammar using, this derivation, which is just represented as a tree, right? So this is parse trees, okay? And then the other thing that you've also seen in terms of context-free grammars is the fact that you can represent them with more standard ways, so with ways that are sort of known as normal forms. So for instance, you've seen the infamous Chomsky normal form. Infamous because it's named after Noam Chomsky, who is a famous linguist and also famous other things. But for our purposes, he's just a famous linguist. He's actually still kicking. I think he's like 95, but good for him. So normal forms are like these sort of standardized ways of representing context-free grammars. So I'm not going to go through, converting this thing into a Chomsky normal form. I can just show you that an equivalent sort of grammar that generates the same language as what we've been talking about so far is something like, S gives you, let's see, X, XB, where X is going to be an sort of intermediate support variable. S can also give me AB. Then X gives me A and then S. And then here A is the variable that I use for generating A, and B is the variable I use for generating B. That is the terminal A and B, right? And so it has to be in Chomsky normal form. Something is in Chomsky normal form if it has production rules that look like either this or that look like, this and then a terminal, right? Or not just a terminal. Oh, yes, a terminal. Yes, a terminal. Yeah, so where A is some letter in T. Okay, so this is like a Chomsky normal form representation of this context-free grammar here, right? And maybe one thing, another thing that you've seen, which is going to be relevant for the discussion of today, is the idea that, if I sort of use now this representation of the grammar in Chomsky normal form to derive A squared B squared, then what happens is I kind of have to start making some kinds of decisions, right? So here, if I want to generate, so let's see. So if I want to generate A squared B squared with G prime, so G prime is now equivalent to G, it's just that it's in Chomsky normal form, then how can I do this? Well, here I replace S with XB. So I replace S with XB. Now, at this point, there's like a choice that I have to make, right? So either I replace X with something or B with something. So, and sort of this idea of having a choice and selecting one of these two options is known as a kind of a derivation form. So if I'm always selecting the leftmost variable, then this is a leftmost derivation. So for instance, here, if I'm doing a leftmost derivation, then I'm going to select the leftmost variable here and replace it. So here I'm going to replace X with AS, so ASB. Now again, if I want to do a leftmost replacement, if I want to do a leftmost replacement, then I have to replace the leftmost variable with what I need to get a square b square. So in this case, it's going to be replacing a with a, and then having SB, SB. So this is known just more formally as a leftmost replacement. Okay, and again here, because I want a square b square, then let's see, I'm going to replace s with ab here. So I'll replace s with ab. Right, again, replacing the leftmost variable. Then, you know, I can keep doing this. I replace the capital A with the little a, the first capital B with the little b, and the final capital B with a letter b. Right, and that's how I derive a squared b square. Using g prime, which is really just g from the start, but in Chomsky normal form. Okay, so far so good. Yeah, cool. Okay, very good. So this is the very quick review of context-free grammars. These things that I'm reviewing are all going to be kind of needed for the sort of proof that context-free grammars and PDAs are sort of equivalent in terms of expressiveness. So the other thing that I want to quickly review is, since you know we have to show that they're equivalent to context-free grammars, PDAs. Right, so a quick review of PDAs. So PDAs are not really language generators. They're more like language acceptors or recognizers, right? So they are language acceptors or recognizers. Right, so in other words, you know, you give them some input and they say, yes, no, is this input in the language I'm trying to describe? So you can actually think of NPDAs, so PDAs that use non-determinism, so NPDAs, as kind of like NFA, which are allowed to have epsilon transitions, which also use a stack, right? So plus a data structure, which happens to be a stack. So that's what an NPDA is, right? So, you know, you have your FA control unit, you have your input tape, like AABB might be on your input tape. But then you also have a stack which you can access and push and pop from. Okay? So that's what an NPDA is. So for example, if I wanted to create an NPDA for the language that I just sort of generated here with this grammar and also with this grammar, then I could do the following. I could say, well, you know, I have my start state Q naught. Then if I read an A, then I'm going to push something onto my stack. And then later on, when I see a B, I'm going to have to pop it because I need an equal number of A's and B's, right? That's the language that I'm trying to accept with my NPDA. So the syntax that I'm going to use for this is, you know, A epsilon X. So what does this mean? This is, you know, I'm reading A. I'm pushing the empty string. So effectively, I'm not pushing anything. So this is the same as pushing nothing. And, or sorry, this is the left-hand side, sorry about that. This is popping epsilon. So that actually means that I'm popping nothing. And the right-hand side is what I'm pushing. So I'm popping nothing and I'm pushing X. So I push X. Right, so effectively what I'm just doing is I'm just, you know, popping nothing and pushing X. So really I'm just pushing X onto the stack. So that goes to Q1. And then what I'm going to do is I'm going to push for every subsequent AIC an additional X. Is there a question? Sorry. It's distracting. Thanks. Okay, so then for every other AIC, I'm going to push another X, right? So at this point, what I have right at this point is, you know, if I have something like A, B, 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 then I'll have something like 3 X's on my stack, right? And the only way for me to accept this string is if now I read a bunch of b's. For each b, I pop an x. And at the end, I see that my stack is back to being empty, or that it actually has the bottom of the stack symbol. Right? Give me a second. Okay, so what I'm going to do is I'm going to, read a b, and then for every b I read, I'm going to pop an x. So I'm going to use this syntax for the transition to Q2. At Q2, for every b I read, I'm going to pop an x. And so I'm going to do this sort of, this state is going to be for pushing an x for every a I read, and this one is going to be popping an x for every b I read. And the only way that I get to an accept state is if at the end I don't have anything else to read, and I have the bottom of the stack marker at the bottom. Right? And so that allows me to go to the accept state. So what we're sort of implicitly assuming, we're assuming that is at the bottom of the stack. When the NPDA begins its computation. Okay, so this is an example of an NPDA that accepts the language. So in this case, the language accepted is, so if this is M, then the language accepted by M is AN BN, where N is greater or equal to 1. Okay, any questions about, yeah? Yeah, what did Jerome say?
The Z naught, which is the start symbol.
Yeah.
Which is what you mentioned. So each time you read, like he didn't, there wasn't any case in his lecture that you can pop the epsilon.
Yes. Okay, this is a good question. Yeah, that's a good question. Yeah, so this is actually really a shorthand. Right, so that's a good point. So this is a shorthand for saying whatever you see at the top of the stack, just leave it as is, but push an extra x, right? So this is a shorthand for saying, if I read an A and I see Z naught at the top of the stack, then push X Z naught, right? So this is, yeah, thanks. That's a good point. And so just FYI, this is like, if you represent this with the sort of transition function formally, then this is delta of Q0, reading an A, having Z naught at the top of the stack, producing Q1, and then X Z naught. Right, yes. So thank you for that. Yes? Yeah, that also works. I think, though, in that case, it's for A and Bn where n is greater or equal to 0. I think. But I can check the slides, because here I'm sort of enforcing that I read at least one A and one B to get to the accept state. It might be that you also had something like this. You had 2 loops here, and then you had an epsilon transition here, and then you were able to go to the accept state here. So it's possible. That's an equivalent way of doing A and Bn for n greater or equal to 0. Yeah. Okay. But yeah, I mean, overall, they all do the same thing, more or less, right? They all accept the same language plus or minus epsilon. Yeah. Right. Yeah, good question. So how does this enforce the fact that the number of A's and B's should be the same? Right? That's the question. Yeah. So for every A you're going to read, right? So for every A you're going to read, you're going to push an X, right? Right? So then, imagine you have like 3 A's, then you're going to push, you're going to push a first X for this A, then 2 more X's for these A's. Now at this point, you can start reading the B's, and like there's nothing else you can do. You have to transition here. So you're going to pop an X for every B you see. And so the stack is only going to return to Z naught if you pop the same number as you pushed, right? And so popping is for the B's and pushing is for the A's, and so that's why it enforces this A and Bn thing. Yeah, yeah. Good, good question. Yes. Yeah, exactly. Yeah. So this would also be, yeah, very good. So this would also be, I mean, I just didn't write it because at this point there's not going to be X on the stack. But yeah, it's also shorthand for AX, XX. Yes. Yes. Good. Already, very good catch. Very good catch. Yes. Oh, that's a very nice question. The question is, can you create an NPDA with a queue instead of a stack? It's a very nice question. In fact, if you replace the stack with a queue, then you actually get a Turing machine. So you actually become strictly more powerful than a PDA with a stack. And so, in fact, this is because to simulate a queue, you need two stacks, actually. So yeah, so that's a very nice question. Yeah, we'll see that later. Well, hopefully Jérôme will show you this later. Good, very good questions. Okay, so hopefully the PDA knowledge is coming back to you slowly but surely. So I just want to also mention the fact that here, this NPDA is accepting via accept state, right? So that's one way. So NPDAs can accept inputs via accept states, right? So how does this work? Well, the NPDA reads the entire word, reads the entire input string, and ends in an accept state. Right, so an NPDA accepts an input W if it reads the entire W, and once it's done reading the entire W, it's taken a path that has allowed it to get it to an accept state, among all the possible sort of branchings, you know, because NPDAs can guess and double check, right? So this is one way. The other way that you've also seen is via empty stack, which is going to be relevant for the thing we're going to see today. So NPDAs can also accept input strings W via what we call empty stack, right? So what are the two sort of conditions for an NPDA to accept via empty stack? The first condition is the same as for the other accepting condition. The NPDA has to read the entire string W. The second condition, though, is now instead of it having to end in an accept state, now NPDAs that accept via empty stack, they don't have any accept states. Instead, the NPDA accepts if and only when and only when its stack is empty. So the stack is empty, i.e., it looks something like this, where Z naught has also been popped. Okay. So a very easy way to sort of convert NPDAs that accept via accept states to NPDAs that accept via empty stack is, you know, you just wait for the NPDA to get to an accept state. And at that point, you create an additional transition that just empties the stack, right? So whatever's left in the stack, you just empty it and you go to a new state, right? So for instance, in this case, we don't really need to do that much. Here we could just say, well, instead of saying, you know, reading nothing, I just keep the Z naught. Here instead, I could say reading nothing, I take the Z naught from the top of the stack and I pop it, right? And so then I just go to a regular state, but now because the stack is empty, once I have pushed and popped the same number of X's for the corresponding number of A's and B's, then I'm going to accept something like A and Bn via empty stack, okay? Yeah? Yeah, that's a very good question. So the question is, how is this example non-deterministic? In fact, this is an NPDA which does not use non-determinism. Yeah, so it's actually a special case of an NPDA. It's a DPDA. So good question. So DPDAs are like DFAs, which can, you know, kind of use epsilon transitions, but only if it's like a deterministic move plus a stack. So the way I sort of intuitively describe DPDAs is just that no guessing is ever done. So I agree with the comment here that, if you look at this machine, it doesn't actually look like the machine is ever going to guess, right? Because, whatever it sees on its input tape, there's only one action that it can take, right? So yes, I agree here. It's actually really just an NPDA that's not using non-determinism, so a DPDA. But you can't always kind of say that the two are sort of going to accept the same thing. So in fact, deterministic pushdown automata are strictly less expressive than non-deterministic pushdown automata. So if you take the family of languages accepted by DPDA, so this is the family of languages accepted by DPDA, then this is going to be a strict subset of the family of languages accepted by NPDA, right? So an example of a language which is in here but not in here is actually the language that contains palindromes, right? So if you take the language L, which is WWR, where, I don't know, W is in AB star, then kind of surprisingly, L is definitely in the NPDA, in the family of languages accepted by NPDAs, but it's not in here. So if you're about to ask me why, I'll leave it as an exercise. That's right. Very good point. Yes. No. The conversion from NPDA to DPDA by sort of subset construction does not really work. Yeah, I could go on a very long tangent to tell you why, but in this case, we're not as lucky, really. Yeah. So it really has to do with the fact that the stack is kind of actually allowing you to have sort of any arbitrary sequence in the stack. So as soon as you say something like, oh, an arbitrary sequence can be in the stack, if you want to sort of represent every possible configuration of the stack with a state in a sort of DPDA, then your DPDA just becomes infinite, and then it just doesn't work. That's the intuitive sort of idea. Yeah. But yeah, good question. Okay. Any other questions about this review? No. Okay, good. Excellent. So hopefully now CFGs and NPDAs are even clearer than they were before for you. Now, what's the connection between the two? You might be asking, what's the connection? Between context-free grammars and NPDA, right? Well, I mean, I kind of spoiled it already by saying what the topic of today's class was going to be. It's that they're equivalent in terms of expressiveness. So what do we actually mean by that? We essentially just mean that if you consider all of the languages generated by context-free grammars, then it's exactly the same as the family of languages generated by or accepted by NPDAs. So the theorem, this will be stated as a theorem. So suppose I have a non-empty alphabet, and let's define the following family of languages. So L sub context-free grammar, this is the family of languages. So it's a set of sets such that there exists a context-free grammar G, which generates the languages in this family. So this is actually also really the family of context-free languages, right? So this is also the family of context-free languages by definition, right? And we also have this other family of languages, L sub NPDA, where, you know, this is again a set of sets, where these sets are languages. And the special thing about these sets is that there is an NPDA M, which, let's just be a bit more specific, which accepts via empty stack. You'll see why I care so much about empty stack in a second, such that this NPDA, which accepts via empty stack, is equal or recognizes or accepts L. So many synonyms. Okay, so this is the theorem. Well, actually, I haven't stated the theorem. I just stated the premise. The following family of languages, then, okay, there's the then these two family of languages is the same. So L of context-free grammars is the same as L sub NPDA. Okay. And so this is, hold on a second. This is kind of stunning. Wait, what, did I make a mistake? Was there a mistake? Oh man, thank you. That would be a kind of a trivial theorem there. Okay, yeah, thanks a lot. So if it was that, then it would not be stunning at all. So, but the theorem as stated now is a bit stunning, right? Why? Because, you know, this wasn't super surprising for DFAs and NFAs because, you know, they were both kind of doing the same thing, and really NFAs were kind of just like a more succinct representation of DFAs. They were kind of just like a more efficient in terms of number of states way of doing exactly the same thing that the DFAs were kind of doing. But now we have like two completely different objects, right? So one is a generator and one is an acceptor. And somehow it happens that they're actually pointing to exactly the same sort of subset of sigma star, or yeah, right? So that's sort of a bit surprising. At least it was surprising when I saw this for the first time, because it doesn't seem like there's an obvious way of connecting these two. You know, for DFAs and NFAs, you know, you have states, and so it's maybe not too hard to see. But for this result, it's maybe a bit more surprising. And so because it's not at all trivial, what we'll be spending today and also Thursday's lecture on, because I'm not going to finish this proof in one single lecture, so I'll leave it to Jérôme to complete it. And so the proof of this is going to be the rest of this lecture. Plus some of lecture 14. Okay, and so I can tell you the overall sort of general ideas for both, and we'll just probably only see one of the two directions. So for the first direction, so if you take L sub CFG and you want to show that it's a subset of L sub NPDA, the idea is essentially what we're going to do is we're going to simulate leftmost. So in fact, we're going to simulate any leftmost context-free grammar derivation using an NPDA stack. So this is going to be the general idea. We're going to see how to do this more concretely in a second. So that's going to be the sort of the first argument in the proof of this theorem. The second one is, you know, to show that L sub NPDA is a subset of L sub CFG. The way that we actually show this is we essentially simulate the NPDA push pop operations via recursively via parse tree. So recursively via the context-free grammar's parse tree. So this is going to be the general idea for both of these directions. Of course, to actually sort of formally prove each of these directions, we're going to have the construction, and then we're going to have like the sort of induction details. I'm not going to do the induction details. I'll leave them as a fun reading exercise. Okay, so let's do, oh, maybe the one thing I'll do before the actual proof is, like what is the general implication? The other thing I kind of want to say. What's the implication of this theorem? The implication of this theorem is, suppose in a question, maybe on a midterm or on a final, you're asked to prove that L is context free, right? Well, now the nice thing is, for sure that you can do either of the two following things. You can either create a context free grammar that generates it, or you can create an NPDA that accepts it. Right, so these are going to be two things that you're going to be able to do to possibly answer this question in maybe some exam setting. Okay, but any questions about the general, what the actual theorem is kind of saying, or it's more or less fairly clear? Okay, I saw one nod, so it means it's maybe kind of clear. Good. Okay, so let's start. With the argument that the family of languages generated by context-free grammars is a subset of the family of languages accepted by NPDA, which, let me just remind you again, right? We're assuming here that that the NPDAs here accept via empty stack. Okay, fairly important assumption to make. Okay, so how are we going to do this? The best way, I think, to actually show this argument is to first look at an example. So consider the following context-free grammar. Context-free grammar G, where it's going to be a single variable, the start variable, and a couple, in fact, three production rules. So S gives you SS, S gives you ASB, and S gives you the empty string. Then what I'm going to try to convince you of is that if you take any leftmost derivation using this context-free grammar, then you can sort of simulate it with the computations of a particular NPDA. So that's what I'm going to try to convince you of. So let's first just consider a particular leftmost derivation. So consider a leftmost derivation for, let's take the string AB. So this is not going to be the most efficient leftmost derivation of the string AB. It's just going to be one that's maybe a bit long just for the purposes of illustration. So I'll start with the start variable S, then I'll replace it with SS. Then because if suppose here I'm going to make a sort of leftmost replacement, then to do a leftmost replacement, I have to replace the leftmost variable, right? So I'll take this S, replace it with ASB, right? So this guy gets replaced with ASB. And then I have the other variable S, right? So this is a leftmost replacement. Then ASBS, that's going to be, if I again need to do a leftmost replacement, let's just replace S with epsilon. So I get AB, ABS. And then again, let's replace, like this S with epsilon, so I'll get AB. Right, again, this is not the most efficient way of generating AB. There's a much more efficient way. You just take S, you go to ASB, then you replace the S with epsilon, right? But it's not going to at all demonstrate the point that I'm trying to make. So that's why I'm using this instead. Okay. Okay, so let's try to see how we can simulate this leftmost derivation, which I'm going to abbreviate as LM derivation. uh, of AB using a stack. Well, in particular, an PDA stack. Okay, so to do this, I've already kind of prepared the general template. So this is the general template. I'll give you a second to write it. Okay, so I've just sort of recopied the leftmost derivation. Now I'm not showing you the state transition diagram yet because I don't want to get too bogged down into the details. I'm just showing you that I have my input tape. So this is my input tape. This is my stack. And then the other thing that I kind of want to consider is what I'm going to pop, push, and sort of read through the computations of the NPDA. Okay. Okay. So I think people have noted this down. So the first thing is, what's the kind of like initial configuration of the NPDA? Well, the initial configuration of the NPDA is hopefully intuitively just going to have the start variable as the sort of bottom of the stack marker, right? So I'm just going to have the start variable S at the bottom of the stack marker. So I'm just going to have S. I'm going to be in a state. It doesn't matter what the state is at the moment. My pointer is just going to be at the beginning of the input AB. And, I'm just like preparing, I'm booting up my NPDA. So this is like the initial configuration, right? Now, what am I going to do? Well, now what I kind of want to do is in my stack, I want to simulate this replacement of S, gets replaced by SS. Well, if S is what's on my stack now, this is kind of like I'm popping S and then I'm pushing back SS, right? So that's what I'm going to do. I'm going to pop S. I'm going to push SS. Because I'm not actually processing any terminals here, I'm just going to not read anything. So I'm not going to read anything. My pointer is going to stay the same, but now my stack is going to have, instead of S, right, I'm popping S, and I'm pushing back SS, so it's going to have S and then S. Okay, so this is the first thing I'm going to do, right? Now, let's see. I want to do a leftmost. I want to simulate the leftmost derivation. Well, it's kind of like for a reason that I'm doing leftmost derivation, because if I take SS and I push it onto my stack, it's the leftmost thing that's going to be at the top of my stack, right? So this is kind of why I'm doing leftmost derivation simulation. So here, to go from here to here, what I'm going to do is I'm just going to say, okay, I'm going to do a leftmost replacement, right? So I'm going to do a leftmost replacement again. So I'm going to do a leftmost replacement. So I'm going to take this S, pop it, and replace it by ASB, which is a rule, which is a production rule in my grammar, right? So I'm going to pop S. I'm going to push ASB. I'm, again, not going to read anything because this is for a leftmost replacement. The reason why I can do this is because S gives me ASB is in the production rules of my grammar. So what am I going to have instead of SS? Well, I'm going to pop this and push ASB. So that's what I'm going to have at the top, A, S, and then B. Okay, so this is, at this stage of the computation, the leftmost replacement, right? Okay, so now, now what I want to do is I want to go from here to here. It's kind of I kind of have a problem here, right? Because I don't have a variable anymore. I have a terminal. So instead of doing a leftmost replacement, I'm going to take another type of transition, which we'll see in the NPDA in a second, which is called a leftmost processing step. So in a leftmost processing step, I'm going to actually consume input from the input tape, ensuring that it's the same as the top of the stack. And if it is, then I'm going to pop the top of the stack, this terminal or this letter at the top of the stack. Yes, absolutely. Okay, so what I'm going to do is I want to essentially get rid of this A, right, such that I can get to the next variable, right? So in the leftmost processing, I process through the actual input. by reading this A on my input tape and also by popping the same thing on my stack. So that's what I'm going to do. I'm going to pop A. I'm not going to push anything, and I'm going to read A, right? So instead of just having A as BS, then I'm going to have S BS, right? Nice. So this is kind of why am I doing this? I'm doing this in order to expose. So why? Why do I need this? To expose the next leftmost replacement step, right? And another thing that this helps do is it kind of helps validate that the NPDA is on the right track, right? Because remember, the NPDA here is just guessing. Like it doesn't actually really know if this is a legit derivation. It's just saying, oh, let's try SS, right? And so the fact that here I'm sort of going to be ensuring that the popping of the A is the same as the reading of the A, this is going to act as kind of a check of the NPDA's guess. So this also, I'm sure, let's see, what happened? Your default, okay, I think that's okay. So I'm going to ensure a match here, a match between the pop and read to validate or to verify the NPDA's guess. Okay, so this is what I'm going to be doing. Okay, so now I did a leftmost processing step. Remember, the reason for this is to sort of expose the next leftmost replacement step. So I can actually do this, right? Like just one thing to mention is my pointer has now moved here, right? Because I just read A. But as I was saying, I can do a leftmost replacement step now because S is at the top of the stack, right? So in this case, what I'm going to do is I'm going to take this S and essentially use the rule that allows me to go here, which is to use the rule S gives me the empty string, right? So I'm going to pop S, push the empty string because I have S gives you the empty string in the set of production rules. And because this is a leftmost replacement step, I'm not going to read anything. Okay. So now at this point, this is what's in my stack, right? And I'm essentially at kind of like this part of the sort of intermediate steps in my derivation, my leftmost derivation. So now, again, I kind of have a problem if I want to do a leftmost replacement. There's a terminal in the way. So I'm going to do a leftmost processing step again, a leftmost processing step. In the leftmost processing step, I'm going to read what's on the tape and ensure that it's the same as what's at the top of the stack. If yes, then I'm going to pop what's at the top of the stack, right? So I'm going to read this B. I'm going to pop it because, I'm ensuring this match in the transition, which we'll see in a second, and I'm not going to push anything. So what's remaining in my stack is just S, right? Okay, and now we're close to the end, which is nice. So the last thing we kind of have to do is, we kind of have to empty the stack because actually, we finished reading the string AB. So we could technically like somehow stop here, but we have to somehow tell the NPDA that we're done, right? And so to tell the NPDA that we're done, we're going to have to, empty the stack, right? So to empty the stack, I'm going to take a final leftmost replacement step. I'm going to use the sort of S gives you epsilon production rule again. I'm going to pop S. I'm not going to push anything. I'm not going to read anything. That's fine because I've already read the entire input string. And so this leftmost replacement step is the final one in the NPDA's computation. And at this point, my NPDA can accept, right? So my NPDA accepts. Because why? Well, because it's read the entire input string. And because the stack is empty, right? Because the stack is empty. So the sort of stacks computation of pushing and popping sort of directly simulated this leftmost derivation of the context-free grammar. Yes.
S, we had to pop the S and push the epsilon.
Yeah.
Why in the final step do we not also have to push the epsilon? Why can we push nothing?
Oh, you're absolutely right. No, because I made a mistake. Absolutely. Thank you very much. Yes. Yes. Thank you. Thank you. Absolutely. You have to push epsilon. Yes. But effectively, if you pop S and then push epsilon, then that's just not pushing anything. Yeah. But yes, absolutely. Very good point. Yes. The last step. So, at this point, right? At this point, I want to finish my NPA's computation and I want to sort of empty the stack. So I do one final leftmost replacement, right? I use the S gives you epsilon production rule. And I say, okay, I'm going to take the top of my stack, pop it, and then push epsilon. But then epsilon, it's sort of like you're representing the stack as a string. So if you push epsilon onto your string that represents the stack, you just have the same thing. And in this case, this stack is already empty. So you have an empty stack. Yeah, nice. Okay. Does this make sense? Yes. 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 Yes.
I'm not really sure how, why why didn't we just push S and not pop?
Why didn't we just push S and not pop?
Because SS isn't in the production rule, right?
Yes.
It is?
Oh, it is. Yes. Yes.
Oh, okay.
Yes. Yes. Oh, that's why.
Yeah.
Okay. Nice. Okay. So good question. I just didn't write it. Yes. Otherwise, you cannot. Otherwise, you cannot. Yes. Okay. Nice. Any other questions? No. Okay. So hopefully this is nice. I mean, kind of a, elegant conversion algorithm, if I do say so myself. Not that I'm invented it, but still cool to present. So, I mean, this is like the intuitive sort of running of the NPDA's computation. What does the NPDA actually look like is the next question. So what does the NPDA look like? Well, kind of amazingly, it just requires a single state. This single state is going to have a self loop. And in the self loop, it's going to have transitions for leftmost replacement steps and for leftmost processing steps. Okay. So for the leftmost replacement steps, what I'm going to do, I'm going to essentially just use the production rules in my grammars as the sort of operations on the stack, right? So just a reminder, the grammar was, S gives you SS or ASB or epsilon. So I'm going to take each of these production rules and place them as the sort of stack operations for the leftmost replacement transitions. Right, so I'm going to have S gives me SS, S gives me ASB, and then S gives me epsilon. Right. So I've covered what the stack pop and push operations are. Now, what is the sort of actually input tape operation? What am I actually going to read? Well, remember when I do leftmost replacement, I don't want to move my pointer, right? So I'm just going to have epsilon production rules here. Okay. So I'm not going to move my sort of pointer. I'm just going to change the sort of composition of the stack. But if I actually do want to read the input, then that's going to be done in the sort of leftmost processing steps. So the way those work is, for every terminal that I have, so in this case, I have the terminal A and the terminal B, I'm going to ensure that when I read this guy, it's because I have the same thing at the top of my stack, right? So I have an A at the top, which I'm going to pop. And if I'm reading a B, it's because I have a B at the top and I'm going to pop, right? And so this is what's doing the sort of, this is what sort of ensures that when you're reading the input string, you're also ensuring that it's the same thing that you're popping, right? So this ensures that the read letter is the same as the popped letter. Okay, and if you're not really convinced that this is actually able to simulate the leftmost derivation that we just saw, well, let's try to do it. Suppose that I had input AB. My stack, the one thing that I forgot to say is that in this case, we're assuming that Z0 is S, right? So the special bottom of the stack marker that I start with is going to be S. So I'm going to start with this, right? I'm going to have S. Then what can my NPDA do? Well, it can guess to take this guy. So it pops the S and pushes SS, right? Then it can use this transition. So it pops this S and pushes ASB. So ASB is pushed. Then it uses this transition to move the needle. So it reads this A, so its pointer goes left, and it also pops this A. So then I have SBS, right? Then SBS, I'm going to use this guy, right? So that's just going to allow me to pop S. So I have BS. Then at BS, I'm reading this B, right? So this also kind of works as a validation of my guess so far. So I have a B and at the top of my stack, and I'm reading a B. So that tells me that so far the computation kind of makes sense in terms of the logic of the grammar. So what I'm going to do now is I'm going to, use this transition, read the B, so move my pointer left, right, and then pop this B. So then I get to the stack, which is S. And then finally, I can use this transition to pop the final S to get an empty stack with the input AB, right? So it does effectively seem like I've been able to simulate the computation of the leftmost derivation of my context-free grammar with this nice PDA, okay? So that's great for this example. Now, some of you might be wondering, well, what's the general construction? So let me give you the general construction. So what is the general construction now that we've seen one particular example? For context-free grammar to NPDA. Okay, so the general construction is going to look like the following. So let G be a four tuple. So it's a four tuple that corresponds to a context-free grammar. Then its corresponding NPDA M plus M is going to be a six tuple. So let's actually do M sub G. So it's going to have a set of states, input alphabet, stack alphabet, transition function, a start state, and a bottom of the stack, special letter, which accepts. So remember, this accepts via empty stack. So we define M sub G as follows. So for the set of states, well, we only need one state. So, very convenient. Q is just a singleton. Then sigma, well, that's just going to be the set of terminals of my context-free grammar. Gamma, that's going to be the set of terminals, union the set of variables. So here I'm kind of overloading notation. So overloading notation. And treating V as a set of strings. Okay, this is a classic move in CS. Then Z naught, the special bottom of the stack marker, that's going to be S, right? And we're always going to assume, right? We're going to assume that MG starts with S at the bottom of the stack. Right, so that's all the setup. Then the actual sort of workhorse of this NPDA M sub G is the transition function, right? So the transition function is going to be taking inputs, Q naught. So I'm not going to say it's any state because, the input state is always Q naught. Sigma as the letter and gamma as the input letter. So sigma, gamma, and gamma. And this is going to return, so we'll define this as a piecewise function. So if sigma is epsilon and gamma is a variable, right? Then what I'm going to do is I'm going to add transitions for all of the production rules that use gamma on the left-hand side, right? So that's going to be a set, right? So NPDAs return sets in terms of transitions. It's going to return, I'm always going to stay at the state Q naught. And if I'm going to pop gamma from the stack, then what I'm going to push is a B, where B is in V star and gamma gives you B is in P. Right, so this is just something like epsilon S gives you SS, right? And in fact, this is the leftmost replacement step. Okay. So apologies for the soups, the symbol of the soup of symbols, the symbol of soups. I can't decide which one's grammatical, but the soup of symbols, yes, that's grammatical. But you kind of have to do this to define a formula. So that's for the left replacement, leftmost replace. Oh yeah. Just to the this. Behind the
Like if you not comma B,
yeah.
like brackets, and
Cool.
to the left of that.
This is a bracket. This? Oh, this is a set. Yeah. Oh, sorry. See, that's what I meant by soup of symbols. Sorry about that. Okay. Thanks for asking though. Okay. So that's for leftmost replacement step. Move this down. And then for leftmost processing step, well, that's if sigma is actually a terminal, right? So it's actually in T. And it's the same. So what we're popping is the same as what we're reading. Then the output is going to be a set, a singleton set, which contains the pair. So Q naught, and epsilon, right? So we're not going to push. Yes, we're not going to push anything. So this is just having something like see A epsilon, right? So this is a leftmost processing step. Okay. So any questions about the formal construction or the example? No. No? Okay. Okay, good. Okay. So maybe just a quick comment on what the proof of correctness kind of looks like. So I'm not going to use it, but I'm not going to show it, but it of course uses induction. So the way that it uses induction is, in two ways. So you have to show that essentially, well, okay. So what you need to show in the proof of correctness is in a given context-free grammar that you're converting, if you have something like S derives in some number of steps W, then this is true if and only if you start in, let me just draw it. So you have your initial configuration. So if your initial configuration is, you have W on the input tape, and you have S as the bottom of your stack, and you have all the transitions, then you're able to go in some number of transition steps to the final configuration, which will look like, reading the entire string, using the rules in the PDA, and emptying your stack, right? So to avoid the soup of symbols, I'll just denote it pictorially, right? So this is kind of what is the statement that you want to show correctness for, so that you can then show the correctness of the construction. How does this actually sort of work? Well, you need to sort of do two things, right? So there's an if and only if here. So one of the directions is by induction. So this one is going to be by induction on the number of derivation steps. And the other direction is going to be by induction on the number of transition steps. Okay, so this is going to be in the slides that Jérôme will post, which will just be a clear sort of a clear write-up of this, hopefully. And it's also in the textbook in case you're curious. And you can also ask me if you want more details. Yes? Yes, you only need one state. Yes, 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 yes.
How does this like want help exit or leave it?
How does it accept or reject input? So we know how it accepts input, right? We know how it accepts input. For instance, this is how it accepts AB, right? Okay.
So, like the only
Well, remember, this is accepting via empty stack. So the way that it accepts, right? The way that it accepts is it reads the entire string and it finds the stack empty. So the PDA does not accept the string if there's no way to like sort of compose these transitions such that you finish reading the string and the stack is empty. So either you like jam at some point and you can't keep going forward, or maybe you finished a computation but your stack still has stuff in it, right? Which would also be a problem. Okay, we can talk more about it if you want. Yeah, yeah, I'm happy to chat. Yeah. No, Q is not accepted. No, right? Remember, just there's no. This is okay. This is important enough for me to write it. See, there's no set of accept states here. States here. We accept via empty stack. Okay. It's fairly important to know the difference because maybe hypothetically maybe someone asks you oh, design this NPDA and make sure that it accepts via empty stack, then you kind of need to know the difference. So yeah. Okay, cool. So it seems like this is okay. So yeah, we're at a bit of a fork here because I can either give you the high level idea of the other proof. Let's just do an exercise. So let's see how this can actually be useful. So how is this construction useful? So how is this construction useful? to the extent that things can be useful in 330. So the way that it can be useful is for building succinct, and really what I mean is, single state NPDAs. Okay, so let's see an example of this where we're asked to create an NPDA which accepts. So in this case, it's going to be specified that it should accept via accept state. So via accept state. For the following language. So the language L here is a union of two languages. So it's the union of the language AN B2N, where N is greater or equal to 0, and the language AM BN, where M is greater or equal to N is greater or equal to 0. And so the question asks us, just create an NPDA which accepts via accept state. I mean, we kind of already know how to do this. So to actually use the conversion algorithm, let's force ourselves to do that by adding it in the question. So by using the CFG to PDA conversion algorithm. Okay. So how am I going to do this? Right? What are the steps essentially to take to solve this question? Essentially, the first thing that I need to do is I need to design a context-free grammar, G, such that L of G is equal to L. Then I'm going to convert G to M sum G, or the NPDA, M sub G, right? And the last thing, because it tells me to create an NPDA that accepts via accept state, I somehow have to take M sub G and convert it to an NPDA that accepts via accept state. So maybe it's good that we're going to re-see this in this exercise, given the questions. And then convert M sub G to an NPDA which accepts via accept state. Okay. So let's see, how are we going to do this? Well, let's do step one. Right, step one, design a context-free grammar, which generates this language. Well, the nice thing here is I have a union of two languages. So if I have a union of two languages, what I can do in my context-free grammar is I can have like a top-level separation, one that's going to go to the generation of, the first language. So let's call this L1, and another one for the generation of L2. So I'm going to have a top-level production rule for S, my star variable, which is going to go to two sort of new star variables, S1 and S2, right? Now, S1 is going to be the sort of part of the context-free grammar which generates AN B2N. So if we kind of try to think about this maybe a bit recursively, right? So what are strings that are of the form AN B2N? Well, the base case is kind of the empty string, right? So I need to encode the base case in my production rules. So let's add the base case. And then what's the recursive case? Well, suppose S1 allowed me to generate something like AN B2N. Then how could I generate a slightly larger string? Well, I would put A to the left and then two B's to the right, right? And that's how I could get AN B2N, right? Okay, very nice. So that generates L1. Now, how do I generate L2? So again, let's start from the second start variable. Now, in this case, let's kind of just notice the general structure of a string that looks like AMBN. So this is a string that has, maybe 7 A's and then, 6 B's, right? So in other words, there's like there's sort of an excess of A's, right? So let's see. If I have something like, I don't know, A, and then BB, well, you can kind of think of the generation of the string as kind of, you generate the matching of A's and B's, and then you just generate the excess, right? So for instance, you could say, well, let's generate A's and B's, right? I'll generate the A's and B's together at the same time. And then at some point, I know that I have to kind of stop and then just generate more A's, right? So what this kind of suggests is, let's first externally sort of generate the same number of A's and B's, right? And then at some point, let's generate the excess A's, right? So to do that, let's just add an additional variable A. And then A is going to be used for like the excess, right? So A is going to give me an excess number of A's. Because this is greater or equal to N, I'm also going to allow the empty string, right? So for instance, if I want to generate, like A4, B2, like I have here, then I can do, S2 gives me A, S2B, then AA, S2BB. And then at this point, I switch to AAA, BB. And then at this point, I can generate any number of extra A's that I want, right? Okay, and so then altogether, this is a context-free grammar G. Let's call this G, which generates L, right? Is this okay for the grammar? Okay, nice, very good, excellent. Okay, so now I've created the context-free grammar. Now let's just convert it to an NPDA M sub G. So for every single production rule, so this is going to be a bit, okay, so let's try to write this as quickly as possible. So let's put all the production rules. Okay, excellent. So I have all the production rules. These are leftmost replacement steps, so they don't read anything. Then for the leftmost processing steps, I only need to consider the terminals here. The only terminals are A and B, right? And this is going to be a single state, right? A single state that loops on Q, right? Okay, so that's step 2. Now, step 3 is I need to convert this to an NPDA which accepts via accept state, right? So I have to somehow add an accept state here. The way that I can do this is I can kind of just imagine that in the computation of Q here, what essentially happens is, I start in my initial config. So in my initial config, I have S as sort of the bottom of the stack marker. I do some things and then at the end, I sort of end with a stack that's empty. So what I can kind of do to sort of add an accept state here is, well, let's just add let's sort of override the bottom of the stack marker and make it something like the $sign, right? I use the $sign because it's never actually used here, right? So if the $sign is below S, then if I, maybe put the $sign in a transition before this, then the PDA is going to be unaffected by the fact that I have this extra symbol. So it's just going to go through its computation, and at some point it's going to end. And now I actually have a way to detect that it's going to end and go to an accept state because I have the $sign that I haven't touched. So that's what I'm going to do. I'm just going to add a new start state. The role of the start state is to go from Q0 to Q, not reading anything, and then pushing the $sign below the start variable S. So S is going to give me S $sign. Then the computation is, going to occur in Q. And then at the end, right, at the end, I'm going to detect that I'm done and that I should accept, right? So I'm going to detect that in my original PDA, I have an empty stack by saying, oh, well, I have the $sign at the top of my stack. So, let's just keep it there. It doesn't really matter. And let me transition with an epsilon transition to the accept state. This works because, if the PDA is maybe a bit too greedy and decides to transition too early, then it still has input to read. So the only way that this accepts is if the converted PDA is sort of able to go through the original PDA's computation, but then at the end transition to an accept state. Okay, let's take a question. Yes? In this case, Z0 is set to S. Yeah. Yes. That's true, yeah. Okay, let's talk about it offline. Any other questions that need public attention? Yes. Yes, you're right, we could. Yes. Okay, thanks very much. Have a nice rest of your Tuesday. Hopefully, I'll see you at the tutorial. Okay. So, you had another question?
Yeah.
Okay, yes.
The $sign,
Yes.
that it's kind of like the Z0, like it's kind of doing the same thing.
Yeah. It's like, yeah. It could just be Z0. It could be Z0 and then Z0, Z0.
And
Absolutely.
sometimes like you don't have to have a Z0 here because it's already like assumed that Z0 is going to be in the back, like from the last video.
Yeah, that's true. So it's what he basically said. You could assume that you have sort of a new definition of your PDA where I don't know, Z0 is, I mean, you could define Z0 as like S and then $sign. Because you have to have S at the sort of beginning here.
Oh, you have like.
Yeah.
Oh,
So
so
you
that's
need-
why you need.
yeah.
Oh, okay, that makes
So
sense.
that's why.
Oh, yeah. That
Yeah,
makes sense.
yeah.
Okay, thank you.
Okay, my pleasure. Yes, hello.
Hi. Could you show me this step again?
Uh,
I was like taking note of these.
yeah, it went a bit fast, sorry.
So-
Yeah, I mean, basically it's at this point, right, if you just have this PDA,
Right,
then the way that it works is it starts with S at the bottom and then it does stuff and then it empties the stack.
yes.
So now what I want to do is I want to kind of detect.
So first of all, for the first of all, we have this,
Yeah,
and then as the last step to convert it to an NPDA that accepts via accepts
Yeah,
it, then we do this.
yeah.
Okay, and how do we do this again?
We just instead of having S at the bottom, we add like a special thing that we never touch here.
Okay,
So we just call that like $sign or Z naught or whatever.
okay.
Then this like computation here that occurs here, right, is kind of unaffected by the fact that there's something below the S now, because it's just never going to see it, right? Like there's no transition here for Z naught.
Right.
So like doesn't matter that I've added it,
Ah,
right?
okay. So okay.
Right? And then it's going to finish its computation at some point. Like if it does accept, then it's going to actually pop. It's going to pop. And then when it pops, for the last time, it's going to detect it, right? By saying Z naught, and then it's going to transition.
Okay,
to accept.
makes sense.
Yeah, okay. Yes, hello.
Question from make like a PDA account. That's like something does not have the and is important.
No, just say something.
Like it can be really,
And in order. Oh, the number, like if it's just the number of A's is equal to the number of B's? Yeah. So
but like it's not like sequence of D A and B like KB and
Yeah.
Wait, can you give me an example? Maybe actually, let's take this outside, yeah? But I'll be with you right upstairs.
So all you will do is take this.
Sorry.
No, you're good. I'm sorry.